Okay, let's look at MathBreeze. I don't think I have anything new here, but we should look at it. 1 second. Just a minute. Okay, so I set the date for the last exam, but we have some assignments due. Okay, on Monday after Thanksgiving, we have 105, 106 from MathBreeze, and also a Weatherly assignment, just a few questions on this. All right, so that's for after Thanksgiving. Okay, so first we're looking at 108. Okay, so we're looking at power series. All right, so power series are series that contain a variable x. So we're looking at power series. Okay, something of this form. So series, but they contain a variable, sort of like an infinite polynomial. All right, and we want to know for what x do they converge. All right, so here we'll do a couple of examples. Here we want to find the interval of convergence. Typically, they could converge for all x, or sometimes no x, or sometimes interval. All right, so let's look at this one. What we always do is the ratio test to start with. All right, so we look at an plus 1 divided by an in absolute value. So in this case, we have x to the n plus 1 divided by n plus 1 squared. And then I'm going to, rather than divide by an, I'm going to multiply by the reciprocal. And then just start simplifying. All right, like here, we can reduce right here. And we have x. And then we can reduce here, and we have, oh, sorry, here we're not going to reduce. Let me get rid of that. We're just going to put one on top of the other and take a limit. Okay, all right, so we're going to have x times n squared over n plus 1 squared. And we can easily show that this goes to 1. So that goes to 1. And so the limit, let's say limit as n goes to infinity, is this. All right, absolute value of x. So in order for this to converge by the ratio test, this has to be less than 1. So need x less than 1 for convergence. So that means the radius of convergence is 1. But we still want to find out what happens at the endpoints when r equals 1. Okay, so that you have to check separately. All right, so in this case, we have that x is between minus 1 and 1. But what happens when x equal 1 and when x is equal to minus 1? So that you check separately. So just when x equal 1, just look at the original series. And when x equals 1, we have the sum 1 to infinity 1 over n squared. And we know that converges by the p-test. 2 is p, and as long as p is greater than 1. So this converges by p-test. And we have the same thing when x equals minus 1. Well, a little bit different when x equals minus 1. We have the sum 1 to infinity, minus 1 to the n, 1 over n squared. And we could easily show that this converges as well. Just the fact that it converges in absolute value shows that this series converges. Remember, if this is true, then this is true. Because this will always be bigger. Here you're adding up positive terms. Here you may be adding up positive and negative terms. So this one is smaller. So if this bigger one converges, then the smaller one converges as well. So this is the absolute value of the second one. All right, so we know that this one converges, so this one converges as well. All right, so that means the interval of convergence, that's what we wanted to find. Is this. All right, let's look at another example. So again, in all of these, we're going to do a ratio test. To find the radius of convergence, always do a ratio test, which we did here. And then whatever result you get has to be, you write less than 1, because for convergence, the ratio test has to be less than 1, so you write less than 1. So if absolute value of x is less than 1, in this case, we do have convergence. And that'll tell you that x converges between -1 and 1. But to see what happens at 1 and -1, you check separately. All right, so let's do another one. We'll do the same type of thing. Okay, let me just turn to the next example. Okay, let's do this one. Okay, so here we're going to do x minus 2 to the n plus 1. So this is a power series centered at 2. The other one was centered at 0. All right, so let's look at this one. So again, first you do ratio test. Always start with that. Okay, so again, that's going to be an plus 1 divided by an. So substitute in n plus 1 here, and we have x minus 2 to the n plus 2. This goes up to n plus 2 over here, and this will be 3 to the n plus 2. And now multiply, instead of dividing by 8 sub n, we're multiplying by the reciprocal. Let's do that. So here's the reciprocal, n plus 1, the reciprocal of this. All right, now we can do some canceling. All right, we have these two powers of x minus 2, and here we're left with just x minus 2. And here we have these two. Cancel, we're left with 3 in the denominator. All right, so now let's rearrange this. We'll put the n plus 1 on top of n plus 2. And what do we have? X minus 2 over 3. And now we're ready to take the limit as n goes to infinity. Okay, I think it's easy to see that this goes to 1. Just divide top and bottom by n, and that's how you show that. All right, so here the limit is this. So we need less than 1 for convergence. So this is what we have, x minus 2 over 3 less than 1. Or multiplying both sides by 3, we have x minus 2 less than 3. All right, x minus 2 less than 3, or just if we open this up further, we have x minus 2 is between 3 and minus 3. And just add 2, so x is between 5 and minus 1. Okay. So this is the radius of convergence is 3. All right, that's the radius of convergence about x equal 2. Okay, so we're talking about convergence about x equal 2. So the radius of convergence is 3. All right, but now we want to see, do we have convergence at 1 and at 5? So we have to check these separately. All right, so let's do that. So we'll check x equal -1 first. And just substitute in x equal -1 into the original. Let's look at the original. Okay, so if we substitute in x equal -1, we have -3 to the n plus 1. So let's write what we have over there. And then the denominator, we had n plus 1 times 3 to the n plus 1, so I'm just going to copy that. Okay, so we have this right here reduces to -1 to the n plus 1. So we end up with -1 to the n plus 1, 1 over n plus 1. Okay, this is an alternating series. And each term goes to 0. The terms go to 0, and one term is less than the one before it. A sub n plus 1 is less than or equal to a sub n. All right, or in this case, 1 over n plus 2 is less than or equal to 1 over n plus 1. So those are the two conditions that we need for alternating series. We needed this one and this one. So this converges. So that's x equal -1. Let's look at x equal 1 now. So let's go back to the original. At x equal 1, what do we have in here? We did x equal 1. I think we want to do 5 now, right? We did x equal -1. Now we want to do 5. Yeah, it's 5 is the other endpoint. Okay, so let's see what happens when we substitute in 5. Then we have 3 to the n plus 1. And here we had n plus 1. And here we also had 3 to the n plus 1. All right, so these just cancel. Okay, so we have this. And we know that this diverges. All right, so we know that diverges because this diverges by the p-test. These two series are almost the same. All right, you would compare 1 over n plus 1 to 1 over n. These are very similar. You can compare them by the limit comparison test. You could do that, or you could do an integral test. And you'll quickly see that this diverges. This is log. Log goes to infinity. This diverges. So those are two different ways of seeing that sum 1 over n plus 1 diverges. But just by looking at it, you should realize that it's almost the same as this one. And you should realize this one diverges because of p-test. So we saw that at x equal -1, we have convergence and 5 not. So minus 1 comma 5. Minus 1 has a closed bracket, 5 open, so that's the interval. All right, that's the interval of convergence. So that's a good example. Very often when you have an alternating series, very often you have convergence at one end and not at the other. Not always, but sometimes. Okay, one other theorem that's at the end here that we're going to use, a simple theorem. Okay, let's say you have f of x equal to some power series. It could be centered about 0 or somewhere else. Okay, and let's say it converges for x minus c less than r, like a radius r about c. Okay. So the conclusion is the derivative you could get by just taking the derivative term by term like you would expect. So you take the derivative like this, term by term, derivative right here, bring down the n, x minus c to the n minus 1. And then also the integral, you can integrate term by term. Okay, a to the n, x minus c, n plus 1 over n plus 1. Okay. You could add a constant onto the end, but I'm just going to do it like this to get one particular integral, one particular antiderivative. Okay, so this is the conclusion that that's the derivative and that's the integral, and it's same radius of convergence. So basically we can differentiate and integrate power series term by term where it converges. So that's what that says. So that's going to be useful in the next chapter. Like, let's just look at, for example, we saw a Taylor polynomial for e to the x. Okay, so this is what we saw that e to the x looks like. We'll see this later. Let's look at this. Let's suppose we look at this particular power series. All right, let's look at this one. We can show, I'm not going to show this here, but we can show that this converges for all x. In other words, okay, so we're not going to show that, but we could show that. Let's look at f prime of x for this example. F prime of x is just term by term. We have n, x, n minus 1. Okay, and here we have n factorial. So what do we end up with? We have canceling over here. Okay, this one is 0 to infinity. Let me just, okay, I'll write 0 to infinity here as well. And here when we do our canceling, we have the following. The first n here, this is n times n minus 1. The first n will cancel with this n. Okay, and this one, the first term drops out when we do the derivative. The constant drops out. So this is n equal 1 to infinity, which is the same as this. So what we're showing here is something where the function, if we look at this series, and we take the derivative, we get the same thing back. That's what we're showing. All right. Well, let's expand it. Maybe it's easier to see if we expand a little bit. Okay, we'll expand a little bit. So this is what f of x is. Okay, here's what f of x is. 1 plus x. All of a sudden it's lagging a lot. Let me just make sure I just want to make sure that I have my cable setting in. I think it's right. Oops. Sorry, it's just that it's, well, we'll see if it stops. It's just lagging a lot when I write. Maybe, it's better now. Okay, it's better now. I'll just write a few terms. All right, we'll take the derivative and we'll see we get the same thing back. Okay, that's 0, and here we have 1, and 2x over 2, 3x squared over 3 factorial, all right, so this is equal to, just simplify it, and we have 1 plus x plus the 3 cancels with the 3, the first 3 and 3 factorial, and we get x squared over 2 factorial. And here the 4 cancels with that first 4, and we get x cubed over 3 factorial. All right, so you see that f prime of x and f of x are equal. So what function do we have where the function is equal to the derivative? That's e to the x. So in fact, this is e to the x. We'll see this later. I mean, we saw that the Taylor polynomial for e to the x looked like this, but the power series for e to the x is this. This is the power series. We'll see that later. But anyway, now I was just showing you I just want to show you an example where we differentiate a power series. So we have this power series. This particular one, when you differentiate it, you get the same power series back. It doesn't change. And that's because that this power series happens to be equal to e to the x. All right, so we can differentiate and integrate these power series. That's the main point here. Okay, so 109 is called representing functions as power series. So let's just review what we did in the previous 3 sections. So the first thing we did was we showed that sometimes we can approximate f of x by a polynomial. And the polynomial, let's say if we're doing it about 0, this is what we had. This is how we approximated f of x by a polynomial. We wanted a polynomial where the first n derivatives agree at x equals 0. So in other words, the kth derivative is equal to the kth derivative at 0. Okay, so this is for k. So we have a polynomial with the derivatives agree, and that's our approximation. So it looked like this: f of 0, and here we had f of 1 x over 1 plus the 0. These are all zeros, f prime. First derivative at 0, and now we have second derivative at 0. And here we have x squared over 2, or we can write it as 2 factorial just to make it look like the other, like the more general term. Then x cubed over 3 factorial, And we do all this all the way up to, if this is the nth, all the way up to the nth term, so all the way up to Fn. So that's the polynomial that we formed for the purpose of derivatives being the same. Derivative of the function is the same as the derivative of the polynomial for up to n derivatives. And they agree at one point at x equals 0. So that's what we did in the first section. We have 3 sections before this. The next section, we looked at power series. We introduced infinite polynomials. So in the first section, we looked at finite polynomials. The second section, we looked at infinite polynomials and where they converged. So we just looked at those. And in the third section, we sort of put these together and we find power series that are equal to functions. So rather than a finite polynomial approximating a function, okay, we're now looking at infinite power series or infinite polynomials equal to functions in specific examples. Okay, so this is what we're going to look at in 109. And we're just going to look at some specific ones that we could find based on some things that we know. So here's the one main tool that we're going to use. Geometric series. We have a formula for the sum of a geometric series. Okay, so remember that. And it converges if r is less than 1. So that's just a fact that we learned about geometric series. So for example, the sum 0 to infinity of 1/2 to the n, so here r is 1/2, is equal to 1 over 1 minus 1/2, or 2. Okay, for example. All right, so it's easy to figure out the sum of a geometric series just using this little formula that we showed. Okay, so now what we want to use this little formula to find a function and its corresponding power series. So we'll start with something very simple. So what we want to do is, in these examples, represent f of x as a infinite polynomial as a power series. And we're going to see how to do this in general, but that's in the next chapter, in 110. But in 109, we only look at some certain examples, some specific examples that we can come up with easily, mainly based on this. All right, so here's the first very simple example. Let's say we have this function. Okay, this looks just like 1 over 1 minus r. We just replaced it with an x. Okay, so we know that this is equal to the geometric series. You know, it's equal to this. I just replaced x with r with x. That's all. And we know that this converges. I'm just for, instead of absolute r less than 1, we have absolute value of x less than 1. So that's our first example. Really, this, just replace r with x. That's our first example of a function. And so this function, 1 over 1 minus x, is the same as this. And we knew that from geometric series. So now we're just going to take variations on this. Let's say instead of a 1 there we have 5. Again, we want to keep coming back to this. This is what we're going to use in all these examples. We want to get this to look like 1 over 1 minus r. So basically we want a 1 here. So let's divide by 5, top and bottom. So if we divide the denominator by 5, we're doing that just so we can get a 1 there. And divide the top by 5 as well. All right. So now we have something that looks a little bit more like this because we have a 1 here. You could just put the 1/5 out in front. All right, and now we can write this as 1/5. I'll leave this on the outside. And here we have, just replace this with the geometric series. Again, use this relationship one more time, except now now we're going to replace r by x over 5. Okay, so this is our r. 1 over 1 minus r, this time r is x over 5. So we have 1 plus x over 5, x over 5 squared. Okay, etc. We could write it as a series like this. And we know that this converges if r is less than 1, or if x over 5 less than 1. Just multiply both sides by 5, so if the absolute value of x is less than 5, we have that this converges. All right, so let's do some more like this. So, we're just going to do variations, and we'll see it's not hard to put this in to get this to look like 1 over 1 minus r. So let's say instead we had 5 plus x. So let's manipulate this one a little bit. First of all, we want minus here. We want something that looks like 1 over 1 minus r. So just write minus minus x. Okay, and now do the same trick we did before, divide by 5. Okay, so now we're there really. We'll take the 1/5 out like we did before. Okay, this looks like 1 over 1 minus r. So we'll use that relationship, that geometric series relationship. So this is equal to 1 plus minus x over 5 squared. Oh, wait, I skipped x over 5 to the 1. So here we have squared. Okay. So let's rewrite this in summation notation. 0 to infinity. And here we have to the n. And sometimes it's written more like this. Let's pull out a minus 1. Sometimes we write the negative separately, minus 1 to the n separately. And in here we can have x over 5 to the n. And again, we have that this converges if x over 5 less than 1. Okay, or absolute value of x less than 5. Okay. So for any 1 over anything linear, we could do the same thing. Let's just, one more example. All right, so this is a more general linear function on the bottom, and I'll just show you how to manipulate this. First, we want a negative, so we'll have minus 3x. And we want a 1 here, so divide by 2. Okay, so we have the 1/2 out in front, and I'll just go straight to the sum notation. All right, so this converges if that's less than 1, just multiply top and bottom by 2/3, or if absolute value of x less than 2/3. Okay, so let's do a little. So here's what we said, that this is equal to this, right? All right. So now let's do an estimate. Let's just check. So sometimes you could just check if this makes sense by estimating one value. So we'll plug something into here and plug the same x value into here. We'll use just a few terms and see what we get. All right. So so let's do that. Let's try to estimate. At x equal 1/3. Well, first of all, f of 1/3, just going straight into our function, not our power series, just substituting in here, we get 2 plus 3 times 1/3. We get 1/3 again. So when we substitute in 1/3, we expect to get 1/3. So now substitute in 1/3 over here, and let's see if we get close to 1/3. All right. So now in the series, now sub x equal 1/3 into the series, into the power series. That's supposed to be the same, give us the same value, into, let's say, 5 terms. We can't, figure out the whole thing, but we'll substitute into the first 5 terms. So here's the first 5 terms. We have that 1/2 on the outside, all right? And we have 1, and this alternates, plus minus. Starts positive, because when n is 0, we just get plus 1. When n is 1, we get a negative. So we have minus 3 over 2x. And then it alternates, plus, and here we have 3 over 2 squared x squared, minus 3 over 2 cubed x cubed, and one more. We said only 5 terms. 1, 2, 3, 4. One more term. Okay. Sub into 5 terms of the power series. So now we're going to sub 1/3 in here. So let's just do that. So here we have 3/2 times 1/3 plus I'm just copying this over. Instead of x cubed, I'm putting 1 over 3 cubed. And here I'm putting in 1 over 3 to the 4th. Okay, see all this canceling that we have right here? We have the 3's canceling, and the 3 squared cancels with that 3 squared. This is 3 cubed canceling with that 3 cubed. This is 3 to the 4th canceling with that 3 to the 4th. So let's see what we end up with. Okay, we want to get something close to 1/3. This is supposed to be equal to 1/3. Just expand that. And change everything to 16ths. All right, so, well, let me do it separately. Here, 8 over 16, and 1/4 is 4 over 16, 2 over 16, 1 over 16. Okay. This comes out to 1/2, and here, add these up, and we get 8, 12, 10, and 1. We have 11 over 16. So we have 11 over 32. All right, so I think you'll agree that 11 over 32 is close to 10 over 30, which is equal to 1/3. So it looks like a pretty close approximation. That's just to convince yourself that this works. All right, substitute in the values, see if you get something, substitute into a value here, you easily get 1/3. That's simple. Substitute into the first few terms. We've picked 5 terms of the series, and we get something close to 1/3, something that approximates 1/3. All right, so just a little exercise to convince yourself that what we're doing is correct. All right, that's all. That's why we did that. So far we can get functions of this form. All right, so far we can write f of x equal to 1 over, let's say, ax plus b as a power series. Okay, within, that converges within, not everywhere, converging within an interval. In other words, it's not as if this is equal to the power series. It's only equal to the power series for some x values. So that's what we can do so far. So far we can take care of this type of function. That's not very much, right? Okay, just, you know, we can write this type of function as a power series. All right, so that's pretty limiting because there are a lot of different functions out there. We only can find power series for these, something that looks like that. But that's all. That's what we can do so far. And what we're going to do in the rest of this chapter is we use the fact that when you take the derivative of a power series, we'll take derivatives of power series or integrate power series to get more power series. So that's what we're going to do in the rest of the chapter. But first, we want to look at one more example. Let me see what number I'm up to. Okay, number 5. Okay. We're going to be using this later, so we want the power series of 1 over x. Now, it can't be centered at 0 because that would make the denominator 0. So we want a power series about x equal 1. Okay. And we're going to, again, go all the way back. Let me just scroll back for a minute. We're just using this again. All right, that the geometric series is 1 over 1 minus r. We're going back to that again for this example as well. So we're going to write 1 over x as, here we want 1 minus x or x minus 1. Okay, start with 1 minus x. We want centered about x equal 1. So here, instead of having an x, we want a 1 minus x or x minus 1. Now you see that if we open this up, what do we get? We get 1 minus 1 plus x. We get x. All right. Now what's this equal to? Let's just flip around the 1 minus x. If we multiply by minus 1. Okay, finally, that's what we have. All right, so we wanted something in the form 1 over 1 minus r. That's what we wanted, but we wanted r to be x minus 1. Okay, so we got that. So now using that formula for geometric series. Okay, so now we're ready to just use that formula. So this is what we have, that this is equal to the sum all right, that's using this formula. Okay, r to the n, sum r to the n is equal to 1 over 1 minus r. This time, so that's what we used here. Okay. Okay, so in our case, r was equal to actually minus 1 times x minus 1. That was our r. Okay, and this is our r to the n. So we're saying that 1 over x is equal to this. Let's just write out what we have here. When n is equal to 0, 0, 0, anything to the 0 is 1. When n is equal to 1, we're going to have minus x minus 1. Okay. When n is equal to 2, it's going to be plus x minus 1 squared. So that's what we're showing. But this is not, we don't have an equality for all x. All right. This is true only if this converges, if the absolute value, okay, so I'll get rid of this minus 1 to the n because I'm talking about absolute value, only if this is less than 1. All right. So that is only if x minus 1 is between 1 and minus 1. Okay, so only when x is between 2, I'm adding 1 to both sides, between 0 and 2. So this only makes sense between 0 and 2. So 1 over x is equal to this, all right, for x only between 0 and 2. All right. Okay. I think we'll just do it on, we're going to be using this a little bit. For the rest of the chapter, we can do something. I'll tell you why we wanted 1 over x. If we integrate 1 over x, we get log x, ln x. So we're going to start with this is 1 over x, integrate it to get a power series for ln x. So that's one thing that we do. So what I want to do, I'll do that next time, but what I want to end with now is just convince you that this makes sense, that 1 over x is equal to this for something between 0 and 2. So what about, let's try x equal 2/3. Okay. So f of x equal 1 over x. We know what f of 2/3 is, just 1 over 2/3 is 3/2. All right, now sub into, let's see, how many terms should we use? Let's say first 5 terms. Of the power series. We want to get a result that's close to 3/2. All right. So here we have, here's our power series. So I'll write down the first 5 terms. Okay, and now let's substitute in 2/3. 2/3 minus 1, that's minus 1/3. And here we have minus the third squared, minus the third cubed. All right, so we have, I'm just going to write this out, 1 plus a third plus a ninth. This is 1/9. This is minus 1 over 27, and we have this minus, so we have, it turns into plus 1 over 27. And this is 1 over 81. Okay. So let's just add these up. This is 81 over 81 plus. This is 27 over 81, that's 1/3. 9 over 81. And here we have 3 over 81. We get 121 over 81 if we add these numerators. Okay. All right, so we want to compare 3/2, that's 1.5. And 121 over 81, let me just do that in my calculator. Okay, I have 1.4938. Okay. All right, so that's just convincing you that these power series this power series does represent 1 over x. All right, so this power series is equal to 1 over x, but only on this interval, only on a small interval. Okay. So I think we'll end with this one. So just to summarize, all we did was find in this, so far in this section, all we did was find power series for something that looks like this. So we found power series. For x in an interval, not for all x. Just for x in a limited interval, we could get a power series for this. We could get this equal to a power series for some x values in a specific interval. So that's what we've done so far, really. We found centered at 0, mostly, and then we did this 1 over x, we found the power series for 1 over x centered at 1, where we just represented 1 over x as, instead of 1 minus something times x, okay, we wanted over here something times x minus 1. That's how we represented it as a power series centered at 1. Okay. So that's all we did so far in this section. We'll continue and find a few more power series by doing things like integrating and differentiating other power series. All right, so we'll do that. We'll do that after Thanksgiving. We'll continue with that. So you have some homework over this long weekend, right? So do the homework, and I'm going to make up assignments for the rest of the sections. All right. And then we really only have one more section to finish the syllabus, and then I think we'll go back and do some of the two optional sections, and that will be it for the semester. Okay. Any questions? Okay, so go over these notes and enjoy your Thanksgiving. All right, and we'll meet again after Thanksgiving.